Welcome to the deep dive. If you spend any time at all pushing the boundaries of reinforcement learning for large language models, you definitely know the pain point.
Yeah.
RL fine-tuning is just notoriously unstable. It's so sensitive to configuration and, often right when you think you're hitting convergence.
It just collapses. The whole thing goes to zero.
Into uselessness, exactly.
It's the perennial problem. And what's so fascinating is that the industry reflex is always to blame the algorithm.
Right, you think maybe my PPO implementation is a bit off or my trust region is too aggressive.
Exactly. But the research we've looked at for you today suggests this instability, it isn't primarily algorithmic. It's not even really an engineering flaw. It's something much, much more fundamental.
Okay, so let's unpack that. The core issue, as I understand it, boils down to this training-inference mismatch.
That's the one.
When we build these modern RL systems, especially for LLMs, efficiency is everything.
Yeah.
So we end up running two separate, highly optimized computational engines.
That's right. You have one engine that handles the fast inference, the rollout.
That's the policy generating the actual responses. Let's call it check.
We'll call it REC. And then you have the second engine, which is all about pure training, calculating those complex policy gradients.
We'll call that PRU. So mathematically, these two policies, tick and pip, they should be identical. They're running on the same parameters.
They should be. But because they use different CEDA kernels, different parallel strategies, maybe even different compilation paths,
their numerical outputs start to diverge.
and that divergence, even if it's tiny, creates these massive problems. It creates a foundational lie in your whole optimization process.
And this is where the really shocking revelation from this deep dive comes in.
It is the source of that numerical divergence, the thing that's actually causing the training to collapse. It's not exotic. It's the widely adopted BF16 floating point precision format.
Wait, hold on a second. BF16, that's been the industry standard for pre-training huge models for years.
I know.
It's used precisely because of its robustness and its dynamic range. Are we really suggesting that the very thing that made our foundation model stable is now fundamentally breaking RL fine-tuning?
That is the paradox. It's a trade-off we just didn't realize we were making. And the solution, it's almost laughably simple.
Which is?
Switch your entire RL pipeline to FP16.
Just switch the precision.
Just switch the precision. This one change, moving from BF16 to FP16, it dramatically improves stability, it accelerates convergence, and it boosts final performance. It often turns a total collapse into a success with minimal code changes.
Okay, that is a huge claim. We absolutely need to understand why that switch works. So let's start with the mechanical instability. Why are the gradients fundamentally biased to begin with?
Well, when you calculate the policy gradient, the theory requires you to sample responses from the policy you are currently training.
From the policy.
Exactly. But for efficiency, we use that separate fast inference engine.
So the responses we actually gather for the optimization step are sampled from the rollout policy, from MNF.
Precisely. And if you then plug those op-sampled responses back into your optimization formula, assuming they came from home, well, you're calculating a gradient that's mathematically derived using the Penghui's probabilities, but based on samples from the engine.
So the gradient is just skewed. It's biased.
It's fundamentally biased. And this isn't just a theoretical problem. It shows up as this painful deployment gap.
Right. So even if we perfectly optimize the model parameters, let's call them, using the training engine.
When you go to deploy that model and evaluate it using the inference engine, the performance just degrades.
The parameters that were optimal for the training environment are not optimal for the real-world inference environment.
And that non-trivial performance degradation is what leads researchers down these rabbit holes of trying complex algorithmic patches. They try to fix the bias gradient using importance sampling.
Right, IS. The principled approach here, for anyone deep in RL theory, involves that sequence-level IS ratio.
You take the probability of the sequence under the training policy and divide it by the probability under the inference policy.
And that reweights the gradient to account for the off-policy samples.
Brilliant in theory. But for LLMs, it's completely impractical.
The sequences are just too long.
Way too long. Hundreds, sometimes thousands of tokens. When you multiply all those tiny probability differences together, the ratio just explodes or vanishes. The variance is so high the estimator is useless.
And that computational catastrophe led to variance reduction techniques. Things like truncated importance sampling, TIS, and masked importance sampling, MIS.
Right. These methods basically put a safety brake on those crazy importance weights. They introduce a clipping hyperparameter, C.
But the source material points out two huge issues with relying on these patches. First is just the computational cost.
It's massive. To calculate that full importance sampling ratio, you need an extra forward pass through the model.
And since a backward pass is usually about twice the cost of a forward pass, you're adding something like a 25% overhead to every single training step.
Just to patch a numerical issue.
And the second, more fatal flaw.
These patches, they fundamentally cannot close the deployment gap. They're only correcting the biased gradient during training relative to the Penghui. They can't guarantee the resulting parameters are truly optimal for the final deployment engine.
You just masking the symptom, not curing the disease.
Exactly. Which brings us past the algorithms and down to the numerical core of the issue, the 16-bit floating point precision trade-off. We need to get into what BF16 and FP16 really are.
Okay, so both use 16 bits of memory, but they allocate those bits differently.
Right, between the exponent and the mantissa. Think of the exponent as defining the dynamic range, the overall scale of the number, like how wide a road is.
And the mantissa defines the precision, how finely you can distinguish between two numbers on that road.
That's a perfect analogy.
So BF16, bfloat16 is the current default. It sacrifices precision for range.
It does. It gives 8 bits to the exponent, which provides a massive dynamic range. That's why it resists overflow and underflow so well during pre-training. But it only allocates 7 bits to the mantissa.
Whereas FP16 flips that script, it's a high precision option.
It uses only 5 bits for the exponent, so its dynamic range is more limited. It can be prone to underflow. But, and this is the crucial part, it dedicates 10 bits to the mantissa.
That's a huge difference in fidelity.
It's 8 times the precision of BF16. You have 2 to the 10 possible values versus BF16's 2 to the 7.
So why does this low precision in BF16 suddenly cause chaos in RL fine-tuning when it worked perfectly for pre-training?
It's the combination of low precision and the architectural differences between RPOM and engines.
Okay.
With BF16's limited 7-bit mantissa, tiny, unavoidable implementation differences, like how a parallel training kernel organizes its math versus how the inference engine does, they lead to different rounding errors.
And since LLM generation is autoregressive,
those small numerical differences accumulate. They compound exponentially across the sequence length.
so the cumulative rounding errors cause the two policies and INTQ to just drift apart numerically far faster than they should. And that creates the huge bias in the gradients.
Precisely. Now, FP16's higher precision, those 10 mantissa bits, they act like a numerical buffer. It just absorbs those minor implementation differences.
So the outputs of the two engines become much more likely to be numerically identical, or at least close enough.
Close enough that the differences don't compound. It prevents the policy divergence before it even starts.
But we can't just ignore the known stability issues of FP16. Limited dynamic range means you worry about gradient underflow, where small gradients just become zero. How do we deal with that?
We use loss scaling, and this is a totally standard, mature technique. It's integral to frameworks like PyTorch.
You just multiply the loss by a huge factor before backpropagation.
Right, it boosts all the small gradients out of that underflow region. Then you just divide the gradients by that same factor before you update the weights. It's a solved problem.
So while B15 became popular because it didn't need loss scaling, the benefit of FP16's precision for RL fine-tuning it far outweighs that minor engineering step.
It really does.
Okay, let's get to the empirical evidence, because the results in the source material are pretty conclusive. They started with an offline mismatch analysis.
A smoking gun. They compared the sequence-level log probability ratio mismatch, a direct measure of policy divergence, and BF16 showed exactly what you'd expect, an exponential failure.
As the sequence got longer, the mismatch got worse.
Rapidly worse. A steep slope of negative 1.01. The errors just compounded fast.
And FP16?
Night and day. FP16 maintained the mismatch at this remarkably low, consistent level. The slope was near zero, negative 0.07. The overall policy divergence was about 24 times smaller than the BF16 baseline.
That proves it right there. It's a numerical fidelity problem, not an algorithmic design problem.
Absolutely. And to isolate this, they ran a clever sanity test using the math dataset, filtering it to keep only medium difficulty problems.
Right, where initial model accuracy was between 20% and 80%, so the task was solvable, but it needed effective RL.
And under the BF16 format, the instability was universal. The vanilla policy gradient methods, and even the ones with corrections like token level TIS, They all just collapsed early.
They hit these performance ceilings like 73% or 88% training accuracy and then just dropped off a cliff.
The most robust one, sequence-level MIS, was the most stable under BF16, but it suffered from this cripplingly slow convergence and still hit a ceiling around 95% training accuracy. The patch was stable, but inefficient and incomplete.
And now contrast that with the simple, unbiased policy gradient estimator, the most basic approach, but powered by FP16.
It just dramatically outperformed all the complex BF16 baselines, reached near 100% training accuracy with no collapse. It solved the problem not with algorithmic gymnastics, but with numerical clarity.
The implications of that are pretty profound. When FP16 was implemented, the source material showed that the performance differences between all these sophisticated RL algorithms, GRPO, TIS, MIS, GSPO, they became almost indistinguishable.
And this is the key insight for any ML engineer listening. When you remove that fundamental numerical bias from BF16, you basically transform the optimization environment into a nearly on-policy scenario.
And in that high-precision world, all those complex corrections?
They offer almost zero marginal benefit because the policy is already consistent.
So they also ran ablation studies to make sure this wasn't just a quirk of one specific setup.
They did. They isolated the training precision versus the inference precision.
And they found you could force stability using BF16 for training, but high-precision FP32 for inference.
But it was totally impractical. FP32 inference was almost 3 times slower. It just destroys the efficiency goal.
The optimal configuration was FP16 for training paired with FP16 for inference.
Lowest mismatch, most stable training, best performance, no speed sacrifice. It's the clear winner.
And this holds up across different model types.
All of them. They confirm the robustness across diverse modern RL regimes. This wasn't just a fix for one model family. We saw superior stability in mixture of experts models.
MOE models, where things like top expert selection must be hypersensitive to numerical jitter.
Exactly. It also stabilized parameter-efficient fine-tuning. BF16-based Loro training collapsed after 600 steps.
FP16 just kept going, perfectly stable.
And whether you're using large, dense models like Qwen 314B or other families like OctoThinker, the conclusion is the same across the board. Precision is the primary stabilizer.
So if we synthesize all of this, the central conclusion for RL practitioners seems pretty definitive.
It is. The instability in LLM RL fine-tuning is fundamentally a numerical precision problem caused by BF16's low fidelity. It is not a flaw in the RL algorithms themselves.
And FP16 resolves this core training-inference mismatch far more efficiently and robustly than any complex, expensive algorithmic patch ever could.
The major takeaway for engineers working in this domain is clear. We have to rethink the precision trade-off for post-training. BF16's huge dynamic range is great for pre-training.
But for the delicate operation of RL fine-tuning, you have to prioritize the critical numerical precision of FP16.
Right. Integrating FP16, pairing it with standard techniques like loss scaling, that provides a foundational and robust alternative for stability.
Which brings us to a final, provocative thought.
This discovery that high precision allows even the most naive, unbiased policy gradient estimator to converge efficiently. It fundamentally resolves that critical bias variance trade-off we've been fighting with under BF16.
So you have to look across the entire machine learning landscape and ask yourself,
what other solved algorithmic issues are we addressing today with these complex, high-overhead fixes, when the real problem might just be a numerical trade-off we inherited from a pre-training default? Maybe we need to shift our focus back from hyper-sophisticated algorithms to just basic arithmetic and precision choices.